So now can you hear me? Okay. So good afternoon to all. We are going to start this part of the course that just to everybody understand what we are doing here is not just a 3 minutes to talk, but 3 minutes to present yourself, your interests, and possibly make during these this almost 2 weeks of course, you do some connections and know new people that you can work with. So make an exchange. Okay. So we are going to follow this presentation order. I would be careful, please, to don't cross too much the 3 minutes time, because then we're going to have problems to everybody to have the presentation. Okay. And we are going to start with Daniel Felipe Suarez Orango. Here. And I will say that the next one is going to be Ellen Vitoria. Ellen. I'm sorry, we are not going to have a moment of questions, okay, now, but we have the cough break later, and you're going to have the whole week to talk to these colleagues, okay? Thank you.
Hello, everybody. My name is Daniel Suarez. I am a PhD student at Universidad Industrial de Santander in Colombia. My thesis is about relativistic models of anisotropic compact objects. I study idealized models of extremely dense star, where the gravity is strong enough to that it is essential. The general relativity is essential in these objects. Um, Also, the internal pressures might depend on directions. Hence, the word anisotropic in the title. Okay. The central problem that I study is that a solution of Einstein field equations are not automatically physical. It might be just a mathematical solution. So my work is to evaluate the physical acceptability of the solutions and see if the solutions are positive pressure, positive density, causality, sound speed less than light speed, for example, and stable configurations. So my contribution to the field is that is a map of constrained physical acceptability models where anisotropy can vary in different models. Okay. Uh, the goal is not only to generate solution, but classify that solution in physical solution that could be a representation of, for example, known pulsars uh, from um, from NICER, for example, for the neutron star interior composition explorer. And that's it. Thank you.
Thank you, Daniel. Thank you very much. Okay. Now Helen and Ellen and Victoria. Excuse me. The next one is Jacinto. I'm going just to.
Good afternoon. Thank you. So my name is Ellen Vitória. I'm from João Pessoa in the state of Paraíba. And my entire academic life has been at the Federal University of Paraíba, the UFPB. So I did my bachelor's and my master's degrees there under the supervision of the professor Paulo Sérgio. And now I'm a PhD student at the same university under the supervision of the professor Carlos Pires. So, as an undergraduate, I studied about some topics such as the physics of the early universe, the inflationary theory, and neutrino physics, but the latter was only from the perspective of quantum mechanics. But during my master's degree, After learning more about the standard model, I started studying actions and action-like particles. So my master thesis focused on actions and action-like particles. And currently, in my PhD, I'm working on flavor physics in the quark sector, but I'm also learning about collider physics. So I have been using some tools such as MathGraph, Pythia, and Delphis with the help of Patricio. I don't know where are Patricio. And I hope to learn more about your researching too during this school, and hopefully have the opportunity to work with some of you in the future in the field of high energy particles. Thank you.
Thank you, Ellen. Okay. Now we call Jacinto Paulo Neto, and the next one gonna be João Vitor Pulhões.
Hello. So, hello everybody. My name is Jacinto. I am postdoc now here. I did my PhD here also, and currently I'm working on this problem called flavor changing currents, basically. And now I'm proposing, together with Yuri, a professor in this event, to build this idea from called flavor changing ultraviolet freezing. And then we want to probe new scale, like new physics, using flavor changing processes, and at the same time try to find the primary space of dark matter. So basically, motivation basically comes from the fact that these flavor changing neutral currents in the standard model, they are very suppressed, and the experiments, they usually cannot reach such very low quantities, let's say. So like, for example, Brinsky ratios. But then if we observe any type of these processes of flavor changing, we expect that it will be new physics. And in this way, we propose that perhaps this type of interactions also involve dark matter particles that was produced through freezing. And that's what we're proposing here. And specifically, this dark matter particle was produced through some type of flavor interaction, and that's why I put a camarão com alho e óleo in this presentation. Shrimps, yeah, garlic and oil. Anyway, so the basic idea of this project is we have a effective operator, and this effective operator can produce dark matter at high temperatures. So we're gonna have both freezing processes, ultraviolet freezing, and also infrared freezing. But but then we compare the production from the UV and the IR, and we discovered that the UV for some T reheating temperature is the UV will be much more strong, let's say. And then we calculated the bounds from kaon decay. So we have kaon decay, the kaon plus decaying into dark matter and the pion. We have long decay into a neutral pion and dark matter particle. In this case, dark matter is a scalar. And basically, that's it. From now, that's what we have. This is not yet published, and perhaps that it will be in the archive in less than a month. Thank you very much.
Thanks, Jacinto. And now we call for João Vitor Milhões, and the next one is going to be José Roberto Alves Moura.
Hello, everyone. Good afternoon. My name is João Vitor. I'm a PhD student at the Federal University of Pelotas, in Rio Grande do Sul. And today I will briefly talk about my project that's entitled Miller-Navellet Jets in Diffractive Process at LHC and FCC Energies. And okay. Then Miller-Navellet jets are characterized by proton-proton collisions, and as a result, we have two jet productions. And the characteristics of these jets is that they have large transverse momentum. Then it allows us to apply perturbative QCD. And additionally, we have a large rapidity distribution that we have to take into account these large logarithms of energy that are directly related to the rapidity. The framework used to perform this resolution is the BFKL, and the basic case of two quark interactions is by the Born-Levi interactions, and as a result, we have a back-to-back process. We have that these both jets are back-to-back, but when we take into account the BFK real gluon emissions, we have that these extra gluons carry some transverse momentum and makes that these jets decorrelate in the azimuth, in the azimuth plane or transverse plane. Then this study was performed formally, but for the inclusive case where we have that these both protons breaks up, and the contribution for this type of observable is applying a diffractive PDF in order that we can measure the proton. Then the observables that we can measure are the integrated coefficients, transverse momentum distribution, and distribution in azimuthal angle. These are some kinematical cuts and tools that I have used to perform these studies. Then here we have the results for integrated coefficients. In this case, we have the single diffractive process where one of the protons remain intact and the other one breaks up. And on the other case, we have the double diffractive event. And here we have these two plots. This left-hand side is for single diffractive, and the other one is for double diffractive. And here we have one of the main observables, that is the azimuthal correlation. And it means that when the rapidity interval is small, we have that these jets are correlated. But when we grow in rapidity interval, we have a bigger phase space that allows more gluon emissions, and as a consequence, we have that the jets gets decorrelated. That's all. Thank you.
Thank you, João Vitor. Now I'd like to call for José Roberto, and the next one's gonna be Kainan Rafael.
Hi. Okay. So, all right. Good afternoon, everyone. I am José Roberto. I'm a PhD candidate here at the Federal University of Rio Grande do Norte. I'm supervised by Farinaldo Queiroz, and what I work in is specializing in direct detection of dark matter in the interface of high energy physics and condensed matter. Okay. So, up. How do I pass? Okay. Thank you. So, what else I do? I've already worked with neutrino mass generation mechanism and some general beyond the standard model physics, including gravitational sectors and detection with the CTAO, a little bit of theoretical models, and my featured project, which is the one I'm going to talk about right now, very quickly, which was my recent contribution alongside Farinaldo, Professor Manuel, which is here somewhere, and Professor Manfred, was one where we used single molecule magnets to detect axions and proposing to detect axions in dark photons. Single molecule magnets are type of condensed matter systems where they have correlated spins, and we can use that because they live in a metastable state when we apply a magnetic field. So this is the result, but very quickly. On the left side, you can see the dark photon bounds in a very optimistic scenario where you can detect it. So that small part there is our sensitivity. And on the right side, you can see the axion bounds that we can have if we use the systems. So that's it. Thank you for your attention.
Thank you, Jose. Now I'd like to call Kainan, Rafael, and the next one is going to be Letícia Guedes.
Perfect. Okay, guys. Hello. It's very nice to be here with you for this 10 days. My name is Kainan, as you can see here in the slides. I wanted to share with you a little bit about my research interests and a couple of hobbies so we can bond a little. So this is me, João and Rogério. João is my main collaborator in the Arizona University, and Rogério is my advisor. I am from IFT. I'm currently a master's student, and my interests are basically cosmology, high energy physics, and gravitation. I'm currently working on what I could summarize as going beyond lambda CDM with field models. So I like to work. I'm currently interested in using field models, either borrowed from particle physics or something, whatever it is, to describe the dark sector. And I got a couple of hobbies, which are basically chess, books. I like to play, and I also like jujitsu. So if any of you guys want to talk about that, please come to me. Please come to me. It would be very fun. As a flash motivation for you guys about my work, so you know, there is lambda CDM, and in lambda CDM, 70% ish of the total energy budget of the universe is basically dark energy, which is represented as a cosmological constant, hence the name lambda. The rest is CDM and something I don't care. So that's it. So got lambda and CDM. And dark energy is compatible with an equation of state, which is this number, which relates the pressure and the energy density. It has to be -1. But recently, Diaz and Desi has been pointed to evidence towards a different parameterization for the dark energy equation of state. And this dark energy equation of state looks very weird. It shows a phantom crossing, and it lives in this very weird and hard to model region of the parameter space. And for that reason, we introduce oh no, my animation is not working. So, okay, so there should be a Lagrangian behind the results where we show a model where we can couple dark energy with dark matter. And in this model, we basically describe the pipeline here where we implemented on CAM and your Boltzmann solver. You have to make some approximations to make sure your fields do describe the cosmological fluids. And in the end, you can actually have a field dynamics. Like we use two different models with different self-interaction potentials for the dark energy sector. And in the end, we showed that a field with these characteristics, with this dynamics, can actually reproduce the W0 WA from DESI and DS at 1 sigma level perfectly. So if you have any interest on that, and if you want to talk about that, then you can come and talk to me. It would be very nice to meet new people and make new friends. So thank you very much.
Thank you very much. Sorry about the animation, but the different. Letícia Guedes, okay. And the next one is going to be Lucas Dumont.
Yes.
So, hello everyone. My first slide is very self-explanatory. So, my name is Letícia Guedes. I'm a PhD student here in Brazil, actually here in Natal at UFRN. And I mostly do phenomenology on particle physics, more specifically collider physics, and more specific, I search for visible and invisible I do visible and invisible searches for sub-GeV dark matter. So just a bit, just a bit of theory. So mostly I work in the light sector of dark matter, the sub-GeV from 1 MeV to some GeVs, but I do assume that they are WIMP-like, so they are produced via freeze-out. That's why we introduce normally a light portal, so we can, go for some outs. So this light portal can be searched for in some colliders and some experiments, just like the NA64, that is a fixed target experiment. And we can have a variety of this kind of mediators. We can also assume a variety of dark matter types. So I work with a bunch of stuff in model building and this part of phenomenology. In the case of NACC4, like this is just a bit of it. It's electron beam, a fixed target experiment of 100 GeV electrons that work that look for, I mean, dark photons and etc. And we can look for via resonant annihilation. This LM is light, dark matter, light mediator, and nuclear scattering with the active target. And this is one recent result. I will use this to say as well that I work with many computational tools. That's other part of my PhD. Right now, I'm working in with Gabi actually in a project to improve and validate one of the packages from Gent4, DMG4, that is used in NACC4 analysis. So with MEDIM and Python fine rules and etc., we can put these black lines that would be via due to the production and the freeze out. And with the DMG4 package, for example, and other things, we can put the sensibility of the experiments. Bell is the visible part, and I mean, yeah, that's basically it. So, thank you.
Okay, thank you, Leticia. So now you call Lucas Dumont, and the next one will be Marcela Gouveia.
Hello, good afternoon to everyone. My name is Lucas Dumont. I'm a PhD student in physical science in Universidad Técnica Federico Santa Maria in Chile. And well, there I am in Valparaiso to get to know me. And my academic background, a brief background of me. My academic focus lies in theoretical physics. I am deeply passionate about fundamental theoretical methods. My previous work was develop heuristic methods for computing the maximal cut in multi-scale Feynman diagrams. I work on Python and Mathematica for have a code to compute these multi-scale diagrams to have some numerical results. My passion about bringing fundamental theoretical research with computational tools. Now, current research, I'm working with Alfonso Cervec in Chile for extending the standard model with a spin 3.5 isotriplet to characterize is a minimal dark matter candidate. I'm currently using a Rarita Schwinger formalins with the Haber-Settle prescription for addressing of shell spurious spin 1.5 to preserve unitary and avoid quantum collapse in high energy. And computational implementation with Lamhen and Feynman rules. Basically, I use only Feynman rules because Lamhen have problems with this spin 3.5 because it's very weird to work with this. So I'm using now Feynman rules to generate Feynman rules because the Lagrangian is ready. So with this, we have the second part that we need to get in CalHEP, so we can compute a cross-section Arelic abundance. And when the first and the second is ready, we can go to micromegas for computation of cosmological observables like relic abundance and the element detection constraint. That's it. And my object to evaluate the stability and phenomenology of this model for a future collider, so I get to know if this is correct or not. And that's it. Thank you.
Thank you, Lucas. Now I'd like to call Marcela Gouveia, and the next one's gonna be Marcos André Moraes.
So, hi everyone. My name is Marcela Gouveia. First of all, I'm sorry for my voice. I got way too excited at yesterday's match. And I am a master's student at the Brazilian Center for Physics Research in astroparticle physics, supervised by Professor Ulisses Barres de Almeida and by Professor Paulo Diomi from NYU Abu Dhabi and Brera Observatory. I am slightly changing the topic here because I'm going to talk a little bit to you about what I'm currently involved with. The main objective of the main object of my current research projects is to research blazars. Blazars are a type of AGN whose relativistic jet is inclined towards the Earth. That makes them bright gamma ray emitters, and also they are candidates for acceleration of cosmic rays. And this is the theme of my master's project. The idea here is to establish a baseline for the Southern Wide Field Gamma Ray Observatory, SWIGO's extragalactic survey capabilities. SWIGO will be a ground-based particle array detector, wide field, whatever, gamma ray observatory installed in Chile. The idea is it should work within the sub-TeV to the PeV energies. And the idea here is we extract the empirical properties of selected sources. That means their spectra and their light curves from Fermi-LAT. That's another type of gamma ray telescope. And with that, we simulate what SWIGO would see to obtain, let's say, a list of potentially detectable sources, and to know which sources we could perhaps monitor to perform real-time monitoring and trigger for pointing instruments such as the CTAO. These are some of the these are some of the results, just so to illustrate what we're doing. Obviously, I'm not going to explain anything or how do we do the simulations and everything. It's just so you can believe in me, believe that I'm doing something. These are the other research projects that I'm working on. The first one, we just released this paper on December last year. Was a reassessment of RFGL gamma ray sources, in which we try to find new blazar candidates using Firmamento, which is a web page focused on blazar research studies. And with that, we found 421 new blazar candidates. You can find the details talking to me or perhaps reading the paper. And I also participate in optical polarization monitoring of blazars with SPARC-4. SPARC-4 is a new instrument that was attached to this telescope over there that I'm right by its side at Pico dos Dias Observatory. It is interesting because it performs simultaneous multi-wavelength polarization measurements. And with that, we can extract properties and about the magnetic field of blazars. And if you want to know more about anything I just said, you can talk to me. So that's it.
Thank you, Marcela. Now I'd like to invite Marcos André Moraes. And the next one is going to be Maria Cecília Santos.
Hello, everyone. My name is Marcos Valiati. I'm a master's student at the Brazilian Center for. Oops. So I'm a master's student at the Brazilian Center for Physics Research, CBPF. I'm mastering in astroparticle physics. I'm supervised by Professor Ulisses Barres from CBPF and Narek Sahakian from ICRANET in Armenia. So basically, I'm working on building an AI tool that can successfully model blazar jet data. this would be a very useful tool because an AI can do this fitting process much faster than traditional fitting methods, which usually takes hours or even days to finish run. So basically, I am modeling a specific kind of radiative process from this kind of source, which is the synchrotron self-Compton model. And I I built a 1 million spectra from this kind of model, this kind of source. With each spectra has uh, 7 parameters. And with this whole 1 million data set, I applied noise and gaps, frequency gaps, to this in order to mimic real Blazar data. And I used this to train a neural network that can successfully mimic Bayesian inference. So with that, oops, so okay. So if that, we can give the spectra of real Blazar data, and it returns me the posterior distribution for each parameter of this model, this kind of model. So the current model we have already successfully fits Blazar data within less than a second, which is pretty much better than traditional fitting methods. And this is the preliminary results, and that's it. If you're interested in that and want to speak about that, I'll be happy.
Thank you, Marcos. Thank you very much. Now we'd like to call Maria Cecilia. Yes. And the next one is gonna be Paulo Andrea Zariuna Calabrese.
Certo. Hi, everyone. My name is Cecilia. I'm from Campina Grande, Paraíba, Brazil. And I have a background in computer science. And I have worked as software engineer for some years before I started my degree in physics. And currently, I'm a master's student in physics at UFCG. And my research is in particle physics and physics beyond the standard model, as there are missing pieces that are not explained by the standard model, such as neutrino masses and dark matter. So we are studying the two Higgs doublet model. That is a model that has two Higgs doublets instead of just one. And it has an scalar singlet and a new Yuan gauge symmetry. And because of this new gauge symmetry, you have a new Z prime boson that interact with the other particles and can be related to some flavor anomalies. Because of this new gauge symmetry, the Yukawa matrices are restricted. So we are studying the two Higgs doublet models, type 1. And it's a model and that the Yukawa matrices do not generate flavor neutral current changes. So we are studying the scalar mixing, this new scalar mixing with the two Higgs doublets and these phenomenological consequences. And we are also studying another models with other Yukawa matrices that generate flavor neutral current changes. And we are validating those models using observables like meson mixing and rare decays and using experimental data limits. And that's it. Thanks.
Thank you, Maria Cecilia. So now we call Paulo André. Okay. And the next one is going to be Rafael Augusto.
Okay. Hello to everyone. My name is Paulo Arelluna. I'm a PhD student from Chile. You know Chile, the very long country. I'm from the north of Chile, a city called La Serena. You maybe have heard about La Serena because there are many observatories at La Serena. But if you don't care about the stars, you may be interested in pisco, a very typical Chilean beverage. And of course, as many of you, I have to move to another city for the sake of science. I'm living in the capital. I don't like it, but I have to do it. And it's my first time in Brazil. And I'm very happy to be here. Now we can talk about science. If I have to summarize my research, would be that question. What can we learn about cosmology with colliders? In order to try to solve this question, I study theoretical models that go beyond the standard model of particle physics. I determine the cosmological implications of these models. And I'm also interested in the experimental sensitivity to prove these models. So we are not also, sorry, we try to explain that matter, but we also try to see something at the experiments. And currently, during my PhD, I'm interested in long particles because they can be connected with reheating and therefore with inflation. So we're trying to do inflation colliders. And this is very interesting, and I'm very interested in discuss these connections between cosmology and collider physics. And I hope we can talk a lot this week. Thank you very much.
Thank you. Thank you very much. Okay. Now we're calling Rafael Augusto, and the next one is going to be Ricardo César.
Hi, everyone. My name is Rafael Augusto, and I am a master student at Federal University of Pernambuco. And my advisor is Bruno Carneiro Cunha. So, I will just a quick introduce what I study. In the early universe, we had the Higgs field, and when the Higgs field, when the universe got colder, and the Higgs field chose a minimum to stabilize. When the Higgs chose this minimum, the Higgs chose one minimal among all infinite possible minimals available to the Higgs. And the question of my research is why the Higgs chose the specific minimal that we already know from the model. So, the goal of my research is to understand the problem and why decide the Higgs that he chose in the early universe. We are investigating this starting use the quark potential and quantum mechanics, not KFT yet, but the thing that we are doing is basically study the phase transition of the Higgs. So we start with the square term of mass negative, and the square term becomes positive in the evolution of the universe. And the main question is that why the Higgs in the phase transition decided that he actually chose in the standard model. So we usually in the books the answer is because yes, but me and my advisor are investigating why the Higgs chose this minimum, and we are using complex analysis, resurgence method. That's a method that non-perturbative sectors and perturbative sectors of the theory, and using a lot of complex analysis like the WKB method to study the energy levels of the quark potential. And I think that's it. I don't put, I didn't put a lot of equation because it's a lot of math physics involved in this work. And I think is that is we so it's a quick introduce of my problem. And if you are free to talk about of these things and others with me. Yeah, I think that's it.
Okay, thank you, Rafael.
Thank you.
Thank you. Now we are calling Ricardo César Silva Rego. And the next one's gonna be Rian Issa Sabá de Oliveira.
Okay, so hello everyone. My name is Ricardo César. I'm a PhD student here at the UFRN. I work primarily with collider physics phenomenology and also dark matter. And I chose here one of the projects that I'm working currently, which is the present limits on simplified SP1 dark matter scenarios. I'm going to give you just a brief overview of the project. So the main goal of it is to go beyond current benchmarks of SP1 dark matter simplified models. Normally in LHC, they use these 4 models, which are in the corner of the slide. But there is no reason for us to keep using these same benchmarks. We can extend them to other scenarios. And that's what we are going to do in this. We are doing this project. So the method is to reinterpret observed limits from Atlas and CMS using a semi-analytical rescaling method, which is based on this package DMWG coupling scan. And this is the method. And the Lagrangian of the model, which is the simplified dark matter model, we have these 2 types. The Lagrangian with the vector interactions and the Lagrangian with the actual vector interactions. In this model, we have Z prime, a massive Z prime, very massive, very massive, and it interacts with the quarks, the leptons, the neutrinos, and also the high particle, which is our dark matter candidate. Okay. In this model, we have 5 free parameters: the mass of the Z prime, the mass of the dark matter candidates, the coupling between the Z prime and the quarks, leptons, and the dark matter. Okay. And also, we are considering 5 different signatures, a lot of analysis, but using these 5 different signatures, which is using the monophoton plus missing energy, monojet plus missing energy, dijet, and the dilepton one. I'm just going to give you some preliminary results here. So as you can see, I choose the dijet and a monojet analysis. In both of them, in both of the graphs, in the y-axis, we have the mass of the dark matter in GeV, and in the x-axis, we have the mass of the mediator. We fixed, in this case, the GL to 0 and the GChi to 1 to maximize the dark matter production. And we vary the GQ, okay? So as you can see, for example, in this dijet search, everything to the right, to the left, sorry, is excluded. So as we increase the GQ, we increase the cross-section, and as this cross-section is changed, the limits is changed, so it increases to the left, to the right, okay? And the same behavior occurs in the monojet case. As we increase the GQ, the limits gets stronger. So we are playing around with this this analysis and to establish different benchmarks and different projects. Yes. So, thank you.
Thank you, Ricardo. Okay. Now we're calling to the lecture of Rian. And the next one's gonna be Telmo Aguiar Garcia.
So, hi everyone. My name is Rian Sassabo de Oliveira. I am an undergraduate student of physics, so sorry if it's too simple. So, yeah. Okay. I am supervised by Professor Alberto Martinez Torres under this project called the three-body dynamics of exotic hadrons. So for us to start, sorry that the layout is a little bit not very good. So according to the conventional quark model, we have we have two types of conventional hadrons that are the meson and the baryon. So this we have the quark and antiquark, and the other we have three quarks, and the antibaryon would be three antiquarks. But we have this question: can all hadrons be described this way? And the answer is no. In experiments such as LHCb, we have discovered many exotic hadrons, such as pentaquarks, tetraquarks, hybrid quarks, and hybrid states, and hadronic molecules. And the aim of this project is to know whether what is the internal structure of these hadrons. And for this, I focus on hadronic molecules, and I use okay, so that's awful. It was not like this when I sent, so sorry for that. So yeah, we start with effective Lagrangians, something called EFT, so effective field theory. We use, that's the starting point. Then we study the two-body interaction using the Bethe-Salpeter equation. Hence, we can study the three-body interaction using the Faddeev equations, and then we can study the dynamically generated exotic hadrons from extracted properties such as amplitudes and go on. So yeah, if you're interested in knowing more about exotic hadrons or asking me why I'm here, you can ask me after this. And yeah, okay, so this is what I just said. And yeah, thank you very much.
Thank you, Ian. Thank you very much. So now we call Thelma Guiar. Okay, and the next one is going to be Viviane Brandão.
Hello everyone, I am Telmo Aguilar. I am from Quito, Ecuador, because this country between Colombia and Peru at the other side of South America. I did my undergrad at the Escuela Politécnica Nacional. I am currently doing my master's at Universidad San Francisco de Quito. I expect to graduate this February. During my undergrad, I study strong decays, where a baryon decays into a meson baryon system via pair creation. So you need to construct an operator that describes this pair creation, and when you apply this to the final initial state, you update the decay width and eventually the mean lifetime. And currently, I am trying to obtain baryon spectra. As we know, the forces between quarks are not perturbative, so to obtain these forces, I propose some phenomenological potentials like this one. And with this, I solved eventually the Schrodinger equation and obtained the masses of various baryons and so on. The idea is eventually to expand this into exotic matter like tetraquarks, pentaquarks, maybe glue balls, but we are working on it. If you want to talk about any of these topics, I am very happy to talk with you, and that's all. Thank you.
Thank you very much, Thelma. Now we are calling Viviane Brandão. And the next one is going to be Joxara. Yeah, next one. Next one.
Good afternoon, everyone. My name is Viviane Leite. I am a master's student in physics at the Federal University of Campina Grande, Brazil. My research is supervised by Professor Francisco Brito, and I also collaborate with Professor Almícar Branquinho at the University of Coimbra, Portugal. My research area is mathematical physics. I work with the Nikiforov-Uvarov method and extensions associated quasi example. And in my work, focus in my work, I focus on quantum systems described by K-deformate potentials. For example, Peugeot-Teller, Wood sessions, and active potentials. These potentials have applications in nuclear physics, molecular physics, and quantum chemistry. The main goal of my research is investigate how Q deformations influences the orthogonal polynomials. That's it. Thank you for your attention.
Thank you very much. Again. And now, Joxara. The next one is going to be Ingrid Ferreira. Next one. Okay.
Hi everyone, my name is Joxara Sanchez Villamizar. Today I try to speak very fast at work based on in this paper. This work is collaborated with in France and Brazil and is looking for a dark matter at LAC, mainly in Atlas group, for specifically analysis beyond the Ricardo talk, beyond the monojet and monophoton searches. When I include the jet and photon and missing energy in the final state, this is the topology where I can find the X1 particle in the final state. X1 is the dark matter candidate in this group. Is the stable particle X2 is the other vector in the dark sector in effective field theory. And the X1 and X2 particle interact with the tensor V. Therefore, if spontaneous symmetry breaking interact with the boson set and photon in the standard model. And the mainly background is any boson plus jet plus photon or boson plus jet boson plus photon. It's clear I can select several cuts in the selection, mainly in transverse momentum of the photon and jet because are the visible particles and missing energy. In this work, I can analyze the several strategies to missing energy, in this case of the S1 particle, and it can obtain the exclude region in collider physics in several analyses. The first one, inclusive signal region and three exclusive signal region. The blue line in the parameter region of the masses of the particle X1 and X2 is the 95 confidential level exclude region. At the band is the 68% of the confidential level. The margin line is the projection in high luminosity. The black line is the exclude region in the freeze out mechanism when I can find the overabundance, the production of the X1 particle. And the this line is the underabundance. It's clear with several strategies you can exclude some region allowed in cosmology in the right plot. What is the main result is I can include several strategies to missing energy to analyze and exclude, obtain the best of the significantly exclude region in collider physics, but it's important to analyze the tails when I try to obtain the validation in effective field theories. Okay, thank you so much.
Thank you, Joxara. And we call now Ingrid Ferreira da Costa. And the next one is going to be Jesus Luke.
Hi everyone. My name is Ingrid Costa, and I will present to you a little bit of my research. It is in viscous cosmological models. And I want to say thank you to the organization for this great opportunity to be here. And I will talk about my academic background first. I have bachelor degrees in physics from Federal University of Pará, master and PhD in physics from Federal University of Espírito Santo, and postgraduate specialization in general relativity from Federal University of São Paulo. My research interests are in cosmology essentially, but in special in viscous cosmological models, cosmological tensions, dark matter, and in large scale structure. But also I have interest in astrobiology and physics education. My current research is in the viscous cosmological model, but it's lambda CDM with viscosity. And in your system, you have two fluids, which are radiation and dark matter. And viscosity emerges from interaction between these two fluids. And you have this bulk viscosity. And then to study this type of thing, you have to a causal theory for dissipative fluids. And then you can analyze the dynamics and cosmic tensions from that. Now, my research is a new theory, a causal theory for dissipative fluids, because the normal one we use is a car theory for fluids, and this theory can be not causal for other systems. So we look for a causal theory for every system you have. And my research perspectives are study these cosmological parameters in this new cosmic frame, viscous cosmic framework, and analyze how cosmic tensions will behave, mainly the Hubble tension and SA tension, and compare these results with the observational data we have already, and if our theory is fitting or not. And thank you all.
Thank you very much, Ingrid. Thank you. Now we call Jesus. And I'm sorry, Jesus Luke do Castilho. And the next one is going to be José Luiz Medina Garcia.
Hello. Hello, everyone. My name is Jesus Luque, and I am a PhD student at the Complutense University of Madrid. And I'm currently working on a thesis on cosmological first-order phase transitions, focusing especially on the phenomenological part. So just as a linear review, a phase transition is a change in the vacuum of the theory. So in general, we have a field trapped on a symmetric potential. But our potential depends on the temperature, so it changes as the universe cools down. This way, at some point, a second minimum develops. And the transition is therefore the change from the former minimum to the new one. But as we can see, both minima are separated by a barrier. So for the transition to take place, the field must tunnel through the barrier. But this is a probabilistic mechanism, and therefore the transition does not take place simultaneously throughout the universe. Instead, bubbles of the new phase nucleate and expand until they collide. So within this framework, so far, I've been studying how particles can be produced during phase or the phase transitions, in particular during the expansion of the bubbles. And we've seen how this mechanism can be very efficient for different types of interaction, allowing to produce very heavy particles, and more importantly, seeing how this mechanism can be efficient independently of the velocity of the expansion of the bubbles. More recently, on the other hand, I've been studying the phase transition during inflation. In particular, I've been studying a two-field inflationary model with an inflaton field rolling down a Stravinsky-like potential and a second spectator field that undergoes a first-order phase transition. Being this phase transition, the mechanism that puts inflation to an end. And well, this is interesting because it allows us to change the predictions for some inflationary observable like the spectra index. And well, finally, I'm also working on a LISA project called Reinterpreting Gravitational Wave Signals from Phase Transitions in Particle Physics Model Parameter Space. So that will be it. Thank you very much.
Thank you very much. And now we're calling José Luiz Medina Garcia, and the next one is gonna be Amanda Guerrieri Melchior.
Well, hello everyone. I'm José Luis Medina. You can call me Luis. And I'm a master's student of physics at the University of Guanajuato in Mexico. So here I give you some pictures of my university. This is the main building, my campus, the logo. And also I give you my email and my ORCID if you want to read more about what I've been doing. So my research topic is ultralight dark matter, specifically boson stars and Proc stars, also known as vector dark matter or dark photons. So I work with this topic in two different ways. One is with stability tests to say something about the stability of these objects and if they can really be formed in universe. So we have two different approaches. One is with numerical evolutions, solving the Schrödinger-Poisson system in the non-relativistic limit numerically. And here you can see a picture of that. You put an initial state and you see how it evolves with time, and you analyze the result. And the other approach is with linear perturbation theory. Here you can solve an eigenvalue problem, and that eigenvalue gives you information about the stability of these states. So here is a picture of the results that my team and I got. And the other way to work with this topic is ALOS formation, because ultralight dark matter is a model of dark matter that tries to solve some curiosities that cold dark matter has on small scales. So ALOS formation is something very interesting to study because it is a phenomena on small scales. And well, here is a picture of that. You can see the formation of a core and a cloud around it of dark matter. And also there are some zones of interference because this ultralight dark matter is made of ultralight bosons. So you can have a wave-like behavior. And well, that's all. I hope that, well, I'm very happy to be here. And I will be very happy to talk with each of you. Thank you.
Thank you very much, José. Now Amanda will talk to us, and the next one is gonna be Gabriel de Souza Fernandes.
Hello, everyone. My name is Amanda. I'm a PhD student at the CBPF in Brazil. I work with relativistic gravity and compact objects, especially with neutron stars oscillations and stability. Neutron stars are compact objects that allow us to study matter and gravity under extreme conditions. Because of this, my work has two main directions. The first is to study dissipative effects on the stability and oscillations of neutron stars in general relativity. And the second is to study neutron star solutions in modified theories of gravity in order to provide strong field tests of general relativity. Therefore, my main scientific question is, how do viscosity, temperature, and modified gravity affect the oscillations and the stability of neutron stars? My recent work focused mainly on this first topic, where we study the oscillations of viscous neutron stars in general relativity. We considered a causal relativistic hydrodynamics theory given by the Israel-Stewart system of equations, which complements the set of equations of general relativity. Here, viscous effects enter as first-order perturbations in the energy-momentum tensor and are described by bulk viscosity, shear viscosity, and heat diffusion. As a conclusion, we obtained that viscosity can introduce additional non-hydrodynamic and thermal modes which have effects on the stability analysis of neutron stars. These results are available in two papers. One was published in Physical Review D and the other is in process of publication. I'm also very interested in the study of neutron stars in modified theories of gravity. A second direction of my work consists in studying neutron stars in scalar Gauss-Bonnet theories of gravity. These theories can predict a new class of neutron star solutions described by scalarized branches in the equilibrium sequence of neutron stars. These solutions do not exist in general relativity, so by doing radial perturbations, we can study the dynamical stability of these configurations in order to know if they could be found in nature. So this provides a connection to strong field tests of gravity. Our work on the second topic is still in preparation. So if you want to know more about my work, we can talk at the coffee break. Thank you.
Thank you very much, Amanda. Now we call Gabriel de Souza Fernandes. And the next one is going to be José Lucas de Almeida Silva.
Hello, everyone. This is beautiful people. Is me. My name is Gabriel Fernandes. I live in Fortaleza, Brazil. PhD student at Federal University Ceará, UFC. Minhas pesquisas de interesse são... Opa! Foi mal, saiu do script. My research interest in general relativity, black hole shadows, ray tracing. My work in doctorate, solutions, general relativity, magnet Z, em compared com Kerr metric, with Kerr metric, by ray tracing. In master, I study tropic gravity and cosmology. I hope to learn a lot, all of you. Thanks.
Thank you, Gabriel. Now we are going to call José Lucas. And the next one is going to be Vitor Pereira.
Hello, everyone. My name is Lucas. I'm a master student in Federal University of Campina Grande. Campina Grande, in English. I study gravitational waves, more specifically, gravitational wave in Horava lift sheet theory. And we study the generation and propagation of a gravitational wave in Horava Lifshitz theory, characterized by a modified tensor dispersion relation. Is this equation 1? We begin by discussing how gravitational waves arise from general relativity through linear Z theory. Write the matrix this equation 2. That is, Tracing is a classical field theory of the field H existing in a flat space-time with a Minkowski metric. From this, we see how a wave equation arises and how the choice of appropriate gauge is simplified this form. Next, we analyze what is happened to conventional polarization states when high-order spatial derivative correction are taken into account. This is a polarization state. This is equation 3. We also constructed the retarded Green's function of the modified wave operator. When Green's function satisfies this equation 5, this is modified operation. And whole solution is given by this equation 6. We also derive the radiation zone waveform to first order in alpha. Finally, we applied the formula to obtain black hole system in a nearly circular orbit and obtain the polarization waveforms for an arbitrary observation direction. So basically, is this. Thanks.
Thank you, Lucas. Now we call Vitor Pereira, please. And the next one is going to be Ana Carolina Oliveira.
Hello, everyone. Good afternoon. My name is Vitor. I'm a PhD student here at UFRN and IIP, and I'm currently working in gravitational wave problems of dark matter scenarios beyond the standard model. And I'm supervised by Fernando as some of the students here, a lot of them actually. So we are looking for gravitational waves because we have a limitation in what we can see in high energy physics due to sensibility, but mainly in energy. We can't achieve the energy that usually we have in the early universe. So the gravitational waves is a really great manner to see very high energy that probably would never reach in universe before and after. So this is a new way to probe it. And yeah, since we are going to have more experiments in gravitational waves, like the Eisen telescope, the LISA, the BBO, and with the results from nanograv, we have the possibility to see a lot of things beyond astronomy and astrophysics. Like, for example, these dashed lines here, they are benchmarkers for models in phase transition with particles in the early universe, and they can be seen by these experiments. So it's a new way to probe the universe in very high energy. That's what we want to. So this is basically what we do. We take a Lagrangian and we perturbate it, and we see everything that we can do with this Lagrangian and calculate the quantum and finite temperature corrections. Then we find the phase transition values and parameters like the percolation, the temperature of reheating, the speed velocity in the medium. And then from this, we take off the gravitational wave signatures. And this is what we do. And in my case, what I do is to add a dark matter candidate. And it's a very rich phenomenology since we can have different manners to put together scalar fields with dark matter. So yeah, it's very rich and very interesting. So my current focus is on stochastic gravitational waves framework, and we are applying different approaches to the phase transition and bubble nucleation phenomena that can be very rich, and also different dark matter scenarios. For sure, I have interest in cosmological phase transition, early universe physics, beyond standard model dark matter, and candidates. So I'm open to discussion. And if you want to take a look at my Inspire profile and enter in contact with me, all of my information is the QR code. So thank you very much.
Thank you, Vitor. Thank you very much. Now we are going to call Ana Carolina. And the next one is going to be Beatriz Marques.
Hello, everyone. I am Ana Carolina, and I am from Rio de Janeiro. I'm completed all of my studies there, and currently I am PhD student at CBPF. I have worked on CONI experiment since my undergraduate studies with Carla Bonifazi and Martin Mackler, and now we developing and improving a convolutional neural network to identify the candidate events to interactions the experiment is looking for. So the CONI experiment is located 30 meters from Angra 2 reactor, and the experiment aims detect for the first time in silicon the coherent antineutrinos nucleus scattering using skipper CCDs. So the exposure of the sensor results in an image with characteristic signature for each interactions. And the Stevens candidates look like point-like charge events, like this. And identify these events is very difficult because other interactions, such as without noise and single electron emission rate, produces similar signal. So we can identify this event through interaction deep because background events occur in the nearest the sensor surface, while Stevens candidates can occur in any deep. So currently, Connie does this with by fitting a two-dimensional Gaussian to the diffusion pattern. However, this method not accurate for few pixels events. So for this reason, we developed a convolutional neural network to identify the interaction deep from diffusion pattern. So we use Keras tuner for selecting the best model and by optimizing hyperparameters, and the CNN was trained using simulated images. So finally, the most recent result shows that CNNs performs better than Coney algorithm with more accurate predictions. So, and if you want to know more about my work, talk to me in the coffee break. Thank you. That's it.
Thank you, Ana Carolina. And now I'd like to call Beatriz. And the next one is going to be Felipe Torres.
Hello, everyone. I'm sorry that I didn't bring beautiful slides with beautiful faces. So my name is Beatriz. I'm from PUC-Rio. I've just started my master's under the supervision of Armand. And during my undergrad, I study about star evolution and how to measure distance through light coming from the stars. Now, I'm focused on atmospheric neutrinos, more specifically for the search of sterile neutrinos, using data from experiments like Super Kamiokande and Hyper Kamiokande. Hope to enjoy the school with you. Thank you.
Thank you very much, Beatriz. Now I'd like to call Felipe Torres. And the next one's going to be Patrick Lemos.
Hi everyone. I didn't bring also a presentation, but my name is Felipe Brendler Torres. I'm in my master's degrees in Catholic University of Rio de Janeiro, PUC-Rio, and my studies are in detection of high energy neutrinos by radio waves, like in the project GRAND. And I'm looking for I'm looking for the potential of future experiments in probing the propagation of ultra high energy cosmic rays and in new physics. Well, I hope I enjoy learning with all of you, and thank you very much.
Thank you, Felipe. Now I'd like to call Patrick. Okay. And Patrick, não sei se é Patrick. And then the next one's going to be Thales Fernandes Bittencourt.
Hello, everyone. My name is Patrick Lemos, as you can see here and here. And yes, I did my graduation at UFRJ, and fortunately, Ana did the presentation before me, so everyone now knows about Connie. He's nearby the Angra reactor, first I work with simulations. My main idea was develop a tracking algorithm for determine the muon flux at the experiment. So here we have an image that we work on from this type of detector that is a CCD, a semiconductor detector. And after I work again with simulations to determine a kind of noise called dark current that this kind of detector had. After changing completely the topic, I think that I needed experience in instrumentalization, nuts and screws. So I work in a laboratory about spectroscopy. I assemble an apparatus to perform an S spectroscopy of the hydrogen. This is an important measurement. For example, a research group earned the Nobel Prize because of this measurement. There, I did the apparatus. I also developed an algorithm to determine the velocity, the temperature, and the velocity of a different atomic beams in the apparatus, and developed again another simulation to determine the efficiency of this measurement. And for the PhD, I work again in Coney with the supervisor Carla Bonifazi, and we are working with something called MCM that are 16 skipper CCDs together. A typical CCD, we have a readout noise of 2.0 electron, and a skip CCD, we have a sub-electron readout noise of around 0.5 electron, 1.15 electron. I also work developing what we call masks that are algorithm that select some regions of the image to remove in order to decrease our dark current. For example, here we have the original image and the region that we remove in order to do this decrease. So as you can see here, first we have this noise, and after that we apply the mask that we developed, we have this line here. As you can see, this is a big difference. So, thank you. If you want to talk,
Okay, thank you.
talk about CCDs, light dark matter, House of the Dragon, we can talk in the coffee break.
Okay, thank you, Patrick. Thales, Fernando. Okay, it's here. And the next one's is going to be Haroldo Bruno Gomes.
Well, hi everyone. I'm Thales. I'm from UF in Niterói, Rio de Janeiro. And well, this is a work developed with my PhD advisor, Rodrigo Sobreiro. And this is published in the Chinese Journal of Physics. And here we basically establish a mapping between two gauge theories. And we do this by noticing that the gauge groups of each theory here, they are isomorphic. So by knowing that, we start with an action of 3D Maxwell Chern-Simons electromagnetism, and we impose our mapping, and then we achieve a 2D gravity with a dilaton, because in Chern-Simons Maxwell theory, we have like this remaining scalar field in the static limit. So we achieve a dilaton on the other side of the mapping. And well, in this work, we also analyze different solutions, and we use Gauss-Bonnet theorem to compute sizes of these spacetimes. And well, besides this works on mappings, I also I'm also interested in two other directions in my research. And well, the first one is asymptotically safe quantum gravity, which is basically a way, an approach to quantize gravity in a non-perturbative way. And I'm heading to Heidelberg University in Germany in October So there I will work with Professor Astrid Eichhorn, and basically the project and the main idea is that working with this scenario of asymptotically safe quantum gravity, we can check the compatible neutrino mass generation mechanisms with this approach. And well, this is the first part, and the last part is another topic that I'm also interested, and it's confinement of quarks and gluons. And I'm working with Antonio Pereira, who is from UF as well. And well, we are starting a collaboration by working on simplified models of confinement, especially using SU2 gauge groups, gauge symmetry. And well, feel free to reach me anytime you like. And thank you all.
Thank you, Claudio. Thank you very much. Now we're going to listen to Haroldo, Bruno, and the next one is gonna be Francisco José Santiago Martinez or Martinez. I don't know.
Tudo bem. Hi, everyone. Good afternoon. My name is Haroldo Moreira, and I'm from Minas Gerais, from Brazil, of course. And today I'm going to talk about a little of my research and my background. So, first of all, I completed my bachelor's degree in UFMG, Universidade Federal de Minas Gerais. And now I'm at ITA in my master in particle physics. So, I'm also a member of the DUNE collaboration. DUNE stands for Deep Underground Neutrino Experiment, and I'm going to talk about briefly about the prototype of the DUNE, the proper DUNE. My colleague is going to talk about a little better than I will. So there's a really pretty picture. Yeah, this is the proto DUNE VD detector at CERN, and this is a LAR TPC chamber, the liquid arc time projector chamber. It's a fancy name for just reconstructing trajectories. And just for context, the Proton VD is trying to test and validate the technologies that Dune will use. So, like, the prototype tries to see if the thing works, the thing work. And my work is in the photon detection system of the Proton VD. So I try to improve photon signal reconstruction, waveform processing, and detector response analysis. Well, I think that's it. Just 2 minutes. Thank you.
Thank you very much, Haroldo.
Yeah.
Thank you very much. So now we're going to call Francisco. Jose? Okay, it's here. And the next one is gonna be Harris Lumengo.
Hello all. I'm Francisco Jose Santiago Martinez. I'm a Mexican student of I'm doing my master's degree at the National Autonomous University of Mexico. I'm also work as TA on the same university. And my work is devoted to measure muons from cosmic rays using the cosmic rays cube. This is a small detector based on plastic scintillators and silicon photomultipliers. This detector was designed by the National Institute of Nuclear Physics at Italy and brought in collaboration to Mexico. With this detector, permanently monitorize the muon flux at Mexico City. And during the last year, we moved the detector to the National Institute of Nuclear Research in Mexico, where there is a nuclear fission reactors. Because my group and me, we are looking to do a neutrino detector based on inverse beta decay. But before we dream about this, we need to know the backgrounds, and one of those is the backgrounds due to muons. So there is a picture of the detector inside the exposure chamber of the nuclear reactor. And there are two plots. This is the summary of what the detector see. Here is the muon flux during the day and the night, because the plot is oscillating. And on the left, there is a spike because during the last year we have a solar flare, and the detector sees it as a spike. I also work with gamma rays detectors, and that's it. Thank you.
Thank you very much, Francisco. Thank you. So we are going to call now Harry. Oh, Domingo is here. And the next one's going to be Sandra Tassiane Carol de Araújo.
Okay. So hello, my name is Aris. So I'm a first year PhD student at LPNHE in Paris. Yes, Aris. And so I'm in the DAMICHEM collaboration, which aim to search for dark matter using CCDs. So our detector has not been yet constructed. It will be located in a mountain between the French and Italian border. And we will use charge coupled devices, so CCGs, to look for dark matter. So when a dark matter particle hits a CCG, it will release charges, and we can measure those charges. And so currently, I am working on the electronics of the experiment, and we will install the electronics and the CCGs at the end of the year, and we aim to start the data acquisition early next year. That's it.
Thank you, Aris. And now we are going to listen to Sandra Tassiane Carol de Araújo, and the next one is going to be Valéria Cristina de Souza.
Okay. Hi, everyone. Okay. Hi, everyone. My name is Sandra, and my presentation today is on Monte Carlo modeling of a two-tone liquid argon test apparatus for scintillation detector (RND). Its work was made possible by the guidance of Francioli Marinho from ITA and the collaboration of Wei Shi from SBU. Well, as we know, DUNI is one of the largest neutrino experiments currently under construction, and it aims to answer some of the biggest questions in physics, such as why the universe contains more matter than antimatter and how neutrinos behave. And to aim this, DUNI will use detector based on liquid argon, and wait. DUNI will use the detectors based on liquid argon and of the large PC type, actually, and the TPC reconstruct in this detector. The TPC reconstruct the 3D trajectories of the charged particles produced in the interactions. So while the photon detection system records the scintillation light produced in liquid argon, since light collection efficiency is so important for detector performance, DUNI is developing new photon detection concepts such as IDPASC, on which IDPASC aims to increase the efficiency by integrating the photon detectors into the field cage. So to evaluate the IDPASC concept, we developed the realistic GN4 module of a two-tone detector, and this module includes the complete detector geometry, including the cryostat, liquid argon volume, field cage, and IDPASC module. So to reproduce the detector behavior, we implemented the optical properties of liquid argon, because we use that, and using the same parameters adopted by LargeSoft is the the official simulation of the Duni. So with the material reflectives and PTP wavelength shifter. With the simulation, it can reproduce the detector behavior, response actually, and on the right we can see a simulated signal obtained from scintillation light detection, and this realistic simulation can provide for us a reliable virtual platform to evaluate and optimize the IDPASC concept before its implementation in Duni. Thank you.
Thank you very much, Sandra. We are going to talk. The expert. So we are going to talk about that. Valeria is here. Okay. And the next one is gonna be Luca Pieroni Pimenta.
Hello, everyone. My name is Valeria. I am a PhD student from Brazilian Center for Research in Physics. I am currently working on within CMS experiment and the precision proton spectrometer, more specifically at the high luminosity LHC phase, and where it is expected to have around 200 interactions per beam crossing, where around 15% of these interactions will be composed by multiple interactions that are not necessarily related to each other, causing a pile-up effect like this, which decreases the efficiency of the event reconstruction. So it is required to enable more adequate detector systems to prepare the experiment for this high luminosity phase. So my work aims to simulate, characterize, and calibrate the hybrid LGAD, what means low gain avalanche diodes. What they are the they are the candidates for these timing detection systems. My work is divided into two approaches: the simulation, where I work with these frameworks. I work with Graph++, Console Multiphysics, Root, and Gent4, where I reconstruct the sensor geometry and simulate the sensor response. And the experimental characterization, where I characterize the sensor and I work with the electronics, where I characterize the ultra-fast silicon detectors. And if you want to discuss more about semiconductors and electronics and computing, coding, coffee, cats, please have a chat with me. Thank you.
Thank you, Valeria. Thank you very much. And now we are calling Luca Peroni. Okay, Luca Peroni is here. And the next one is gonna be Gabriel Oliveira dos Santos.
É isso mesmo. Só que não era para ser pequenininho no começo, mas tudo bem. Hello, my name is Luca. I'm 18 years old. I'm I'm an undergraduate at University of São Paulo. I'm studying mechanical engineering, and I'm still not a researcher. I hope I will be a researcher in the next years. I love astrophysics since my 9th grade. I've been studying it for competitions. In my 2nd grade, I went to Costa Rica for the Latin America competition, and in my 3rd grade, I went to Mumbai, India. And today I'm currently working with the Olimpíada Brasileira de Astronomia, Brazilian Olympiad of Astronomy and Astronautics, to produce the tests in astrophysics and that data analysis, observational astronomy. And I'm here because I'm trying to be inspired by all of you and all the lessons. I'm not sure if I will do research in this area. I hope I will, but I need to be sure first. So I'm here to see all of you guys. I'm very interested in cosmology instrumentation because it has something to do with mechanical engineering and space habitats and dynamic control for satellites, which I'm working a bit in University of São Paulo in the satellite group, and I'm pretty happy to be here and meet all of you. Thank you.
Thank you very much, Lucas. So the next one's gonna be Gabriel Oliveira, and yeah, I'm sorry. Now we have Gabriel Oliveira. No, it's Luca Pimenta. Não, é Gabriel Oliveira. And the next one's gonna be João Paulo.
Então vai ser o.
Hello everyone, I'm Gabriel from USP, and my advisor is the Marculate. So my research is search of non-resonance production of Higgs pi in the BB tau tau channel at Atlas B Foxtree model to ZZ and TT bar background. So why to Higgs? The Higgs field play the role of the electroweak symmetry can be break and the generation of the mass of the particles, and we studied the self-accouplement to Higgs field in the lambda. No, is lambda Downbarian is lambda 888, but not the slides don't work. So how to measure the self-complement? So we have three types of the leading order, next leading order, and next to next leading order. So this, my work is about linear order with 19% about the most dominant by gluon fusion. We can use também to vector bosons fusion, but my work is only the gluon fusion. So we have these two diagrams, Feynman diagram. So the box diagram, so is the gluon fusion. In this key is probably the quark top and the K22 Higgs, and we have the triangle is the gluons and loop to top quark and virtual Higgs and the K22 Higgs, and this dot red is the self-complement. So if is equal to 1 is the standard model is okay, but if is the other number is below the standard model. So how to calculate the probability to find the stage of the Higgs? So we have this the case. So my work is about this 7.3% because you can see, okay, why don't use the BBBB? Because it's the more probably to detect, but it's a full hadronic. So to separate the background is very, very difficult because CD Mutzet. So you can see, okay, the Atlas have a good photon detect, but with this we have a BB gamma gamma channel, but it's very, very hard to detect. 0.76%, and the median of these two channels is the BB tau tau. When you have have a BB channel, so have a good probability, and tau tau is leptonical, so it's not so full hadronic, but we have a difficult with the backgrounds. So we have two, more than two backgrounds, but the two principles is the top TT bar. So the TT bar they can decay to the W boson. So with the W boson full with very PT have a fat jet and the W boson decay to B jet, and the irreducible ZZ backgrounds, so decay equal to the Higgs, so decay to BB total. And how I use to separate the background with the signal is about neural networks. So I use the graphic neural networks. So the node is the moment of the particles, and the edge of the graph is a detector, or is a geometry of the detector. And these cool images is the full architecture of the model. And we have a good result. So 99.99% of the TT bar is rejected to the model. The ZZ is 99%, and unfortunately, it's 16% of the signal is rejected too. But I am working now to minimize this. And this figure is before they separate. So you need believe in me, but here have the signal, but so in editing, unfortunately, I can show the plot of the separate because it's the from Atlas member. I don't can show these results. And thank you. If you need help with neural networks, can talk to.
Okay, thank you very much, Gabriel. Now João Paulo will speak first.
I don't have a slide. Yeah, I don't have a slide also, so sorry. My name is Paulo. I have a degree in computer science, another in physics. I was out of academia for 10 years working on defense slash aerospace industry, or mostly writing computer vision models and flight algorithms, especially to see in the sand. If you know, you know. And I went back to the academia last year, finishing my degree, my master degree in aerospace engineering, working mostly with developing small CubeSats with detectors in space, like radio telescopes. I also work for the SETI Institute, so I'm paid to hunt aliens. I work on the real research, looking for FRBs, fast radio bursts, and techno signatures, as well as pre-bio signals using the Allen telescope. So I'm currently working on the Hat Creek Radio Observatory. So yeah, I'm a machine learning guy there. I do everything machine learning related, and I'm getting ready to start my PhD in astrophysics in October with them. Yeah, thank you.
Thank you, João. Thank you very much. The next one is gonna be Laurato Silva. Okay, Laurato is talking to us now, and the next one is gonna be Erzen Tunch.
Hello, my name is Lautaro. No problem. I'm finishing my master's in Buenos Aires, and I work in ITEDA, an institute related to the Nuclear Institute of Argentina. And I work in the Pierre Roger Observatory. I work mainly related with the muons that the observatory measures. So in that sense, I'm going to talk a little bit about the different detectors the observatory has. It has essentially, it's a hybrid detector or observatory in that sense. It has two main detectors, the surface detectors and the fluorescence detectors. The surface detectors measure particles directly as they emit light via Cherenkov when they pass through the water that is inside of the tanks. And the fluorescence detector is strictly a fluorescence telescope that measures the light produced by the ionization of nitrogen on the atmosphere as particles and the extensive air showers traverse through from the top of the atmosphere to the ground. However, in the past couple of years, the new detector was developed and installed in some of the stations around the observatory, and that is the underground muon detector, and that is the detector I work with. It measures muons directly, and how does it do it? It is buried 2.5 meters below the ground, so it's in that sense it is unbothered by the electromagnetic component of the showers, and it measures essentially only muons. And what I do is I am studying the azimuthal asymmetries that this detector has. This is extensively related with the geometry of the showers, and also with the phenomenology that muons and compared to the electromagnetic component of the showers develop as they reach the ground. What I try to do is measure this laterly asymmetry, and what I try to see is plots similar to what you are seeing on the right. So that is what I do. If you have any more questions, I think I have a poster. I will have a poster eventually. And I think that's it. Thanks.
Okay. Thank you very much, Lautaro. It was written wrongly here. You see. So, Oxygen will talk to us, and the next one is gonna be Roberto Alexander Servino Cortines.
O screen? Ai, cadê? Enter.
Hello, my name is Tunç. I put something like here to maybe it's easier to see it like this to pronounce because it's every time it's difficult for people. So I'm from Turkey. I'm doing PhD in UFES, Universidade Federal do Espírito Santo. My supervisor is Valerio Mara. I'm almost finishing my PhD and I'm mostly working in numerical cosmology. I will talk about the emulator project. This is my PhD project we do. This is a gravitational lensing emulator project for point sources like supernovae. So, gravitational lensing, normally it's like distortion of the light on the way to the observers. So there's a structures in the middle, so light gets banded, distorted, defected by this medium in the middle. So how you can treat this? How people study this? There's a Gaussian noise treatment. People model this lensing effect as a Gaussian. Here I try to show that it's not a Gaussian. So this is an approximation. What can you do better? People can do theoretical models that can be Swiss cheese model. Can be there's also something called meatball model. Then there's another way to do it, like you can do simulations. You can do simulation boxes, then create the density map of the area. But this is very heavy. So the emulator idea is that we have some simulations. We try to get the statistics without going the simulation path all the time. So yes, we do some simulations with technologies, and then we have some parameters, targets to model. Here we use like XGBoost machine learning model, and then we predict this here. Like there's 4 parameters, we are 4 values we are predicting. Then we recreate our statistics from these models. So the emulator-based model is like it's low cost, fast, and very flexible. You can do different cosmologies in a range. It's good enough approximation. It's not like very high accuracy as simulation itself, but it's a good enough way to do it. So this is a published work, so it's in already publicly available in GitHub. So next thing we should do is to use this in an MCMC, to parameter extraction model. So basically, normally this lensing effect is, as I said, it's treated by a fixed Gaussian. And there's we've created 4 models. So there's a fun fixed reference model. The other one is you can predict the Gaussian with the emulator, or you can add non-Gaussianities with an expansion, and or you can do a full convolution, full treatment of lensing PDF. So okay, this is the thing. Now these days I'm try to do this MC analysis, then so results will be available soon. And that's all. If you want to talk about these applications of any other way to applicate this emulator, I will be happy to discuss. Thank you.
Thank you very much, Tunch. Now I took it properly. And we'd like to call Roberto Alexander. Okay, and the next one is going to be Tiago de Andrade Rangel Monteiro.
Tiago. Nice.
Hello, everyone. My name is Alex Elviño. No, it's just one. I am a PhD student in the Complutense University of Madrid. Currently, my research is focused on the high energy areas, mainly in the Cherenkov telescopes and the Cherenkov telescope array. One of my research lines is the use of convolutional neural networks for the reconstruction of the Cherenkov events, the showers. Mainly, what we want to reconstruct is the direction of the rays, the type of the ray, if it's gamma ray or cosmic ray, and also the energy of it. And with the CDR packets, what we are doing is to try different architectures like PyTorch and TensorFlow, and also different techniques like transfer learning or attention approaches. Also, another of my lines is I am a maintainer of the LST-1 telescope on-site analysis, the first large-size telescope of TTA. And with this pipeline, what we do is to get from the raw waveforms that we get with the telescope, we follow all the data levels to get the calibrated images that the scientists are going to use the day after the data is taken. And finally, in the most scientific part of my PhD, I do indirect search of dark matter, and now I am one of the main developers of the dark matter module of GammaPy, which is a package that is well known in the high energies field, and is going to be the standard for CTA analysis. And but my main effort is on the dark matter module. So that's it.
Thank you, Alexander. Thank you very much. Now, Tiago de Andrade. And the next one's going to be Veronica Casola.
So, hello everyone, my name is Tiago. I'm a master's student at the State University of Rio. I'm doing the supervision of Professor Gilvan Augusto Alves and Professor Elisa. And I have been working on two primarily things that are angular analysis of rare decays, of B0, and also simulation and instrumentation of RPC detectors. So, these rare decays, we can measure them by a FCNC process, which is our flavor changing neutral currents. And in the standard model, they are basically really suppressed. So the order of the branching fraction of this process is around times -6. So they are highly sensitive to new physics, and they occur only basically in these two diagrams here, in the penguin diagram and the box diagram. So they are basically rarely suppressed, also because of the Kobayashi-Maslow matrix, and also because they are loopy diagrams. So since the 90s, we have been in a very good excitement, because we have some deviation from the standard model that are the flavor and universities, the decay rates, and the angular observables. So recently in 2022, we have a better agreement in the lepton flavor universality, but we still have some problems to describe both the differential decay rates and the angular observables. I'm focusing here on the angular observables since we have a 4.2 sigma deviation from the standard model, and that's basically one of the most inspiring things to look at to search for new things. So we can describe the angular decay rate by basically four variables. One of them are the diamond mass of the system, and also three other variables that are the angles that are described in the topology of the events. So basically, we can create this formula here, which is the branching ratio, and then we can have only two meanings, physical meanings, the fraction of longitudinal polarization of the K star, and the forward-backward asymmetry of the dilepton mass. So the other part of my master's degree is the construction of the resistive plate chambers, which are muon detectors, basically, primarily. So I have been working on these since my summer student at CERN. So I have been working on ways to change the gaseous mixtures of the detector. So we are trying now some other things because they are really way better for the environment as well. So the RPC detector, primarily, we have a muon passing through the detector. We have the primary ionization, the avalanche process, and then the final the signal induction from our detector. So basically, that one here is the photo of a small prototype of the RPC detector that we have in the CBPF laboratory. And what I want to do, sorry, because this was supposed to be an animation of the avalanche process. And since I'm trying to do is simulate the response of the detector. So here are some of the primarily results that I have from the signal process, the charge induced, and some of the efficiencies that I'm trying to simulate those plots right here to try to modify the concentration of CO2 in the gaseous mixtures. So this is it. So if you have any questions, please talk to me.
Okay, thank you. Thank you very much, Thiago. Now Veronica is going to present herself. And next one and last one is Lucia. Silvia.
Good morning to everyone. I'm Veronica Cazzola, and I'm from LPNHE in the Sorbonne University in Paris. But as you can clearly heard, I'm Italian. And I'm currently working on the electric field studies in the dark matter sector. During this year, I have the opportunity to be in the two collaboration. The first one is Xenon, and the second one is XLZD. Xenon is the current experiment for dark matter direct detection, and XLZD will be the next generation detector. Both of them are based on the same principle. We have the experiment that is hosted under the mountain to reject the background and have less interaction from the atmosphere. And inside there is a part of the veto for muon and neutron. And inside there is the main detector that is a dual phase TPC. This means we have a structure inside composed by different electrodes that can create an electric field inside. And especially we have two parts. The first part, the main bulk, is composed by a drift field, while in the upper part we have another electric field that is called the extraction field that is higher. And this permits the creation of two signals when a dark matter particle interacts inside our system. In this case, we are using xenon in dual phase. So this means liquid xenon on the lower part and gaseous xenon in the upper part. And we have an array of PMT to read the entire signals. XLZD is based on the same idea, and I'm also currently working on this R&D project for the next generation detector. This facility is hosted at LPNH and is a prototype. So we can see also here the main detector, the TPC, and we have all the cryogenic system. Here there is liquid nitrogen and we are working on cryogenic temperature. And the other parts are related with the electronics and the gaseous and vacuum parts. Okay, for the first part, so the Xenon collaboration, I'm currently doing some electric field simulation because now we are doing a new S-run, science run, and this implies a new geometry in our detector. So I started using this program called the COMSOL Multiphysics to implement this new geometry. And here you can see an example for a 2D simplification of the system. And then I also started to study the best configuration to having the best electric field inside, so tuning the different voltages for the electrodes and for the PMTs and the entire structure to create the drift. Then, using my results from the console simulation, I can also develop some codes using Python to study the main parameters related with the drift. So, like for example, the charging sensitive volume. The part in which if you have an interaction, you could not create a signal because the charges are lost. Or, for example, the velocity and drift time, the diffusion coefficient, because when we have an interaction from the dark matter particle with the xenon, the ideal trajectory is straight, but in reality we have a material inside, so there is diffusion. And so this can create a dispersion in terms of position, and this implies also a not proper reconstruction of the signal and the position of the interaction. And regarding my studies in my lab at XELab, as I said before, we have these electrodes inside our detector, but are very big, and we will bigger in the future. We are talking about 3 meters diameter, and this has some issue because there are some forces that are acting inside, like thermal, electrostatic, and gravitational, and this can create some sagging and deformation. And this implies having not correct signal reconstruction, hotspot that can create discharges and so ruin also our detector. And the idea is to create this new configuration for the electrodes. Especially, I'm talking about a new mesh composed by hexagons and with some structure like pillars that are inside the two electrodes on the upper part, so between the gate and the anode. And this implies having uniform field, not having the instabilities from the mechanical point of view. What I'm currently doing is design these electrodes starting from the draw in COMSOL. So I'm trying to replicate our real TPC and studying the mechanical and electric behavior inside the detector. Here you can see some my first drawing. This is an example, and now we have to continue and find the best configuration for the shapes, for the materials, to avoid all the problems that can be related. And we are also starting these are the first prototype we got the past month. And we are also trying to study the impurities to avoid the possible discharges and so on. Thank you very much.
Thank you very much, Veronica. Now I'd like to call Lucia Silva. That's going to be the last presentation. Then we have the coffee break.
Hello everyone, I am starting too, so I will kill this very quick. I'm Lucia Angel. I am Colombian, but I came to Brazil to pursue my master and PhD. I did sandwich period in the University of Oslo, and my supervisors are Farinaldo da Silva Queiroz and Torsten Brindman. My PhD has been basically based on dark matter phenomenology, and I work in different things. In the case of WIMS, we have worked with indirect detection searches that basically we are interested in the products of decay or annihilation of dark matter in the region of GeV. I am part of the CTO collaboration. So basically, what we have done until now is study effective field theory and relate this with the sensitivity of the CTO that is under construction. I have also worked in VV and constrained new physics in different physical phenomena, for example, the gravity no problem. And lately, I've been interested in LiDAR sectors, particularly in the search for action-like particles, dark photons, and actions. This is my inspired head if you want to check my profile. And the main current projects that I'm working on, it's been, for example, one that is related with operators 7 and 8 in effective field theories. We constrain this with CTO sensitivity. We are expecting that this is approved by this collaboration, and we will publish it soon, as it's finished now. I am working too in cosmological constraints of dark matter candidates produced for a specific production mechanisms that is called exponential growth mechanisms with people from University of Oslo. And we are developing a Monte Carlo tool in order to simulate the collision terms in this specific production mechanisms. Other project that I will show in the next slide is basically the experimental setup to produce dark photons. It will be the first time the detector that for first time will be based here in Latin America. Is accelerator based experiment. And the last one that I'm working now is search for LiDAR sectors in reactor neutrino experiments. In this case, with the collaboration of CONUS and CONI. CONUS is with the people from Max Planck Institute, and CONI with the people for UFRJ. Basically, regarding to the experimental setup to produce dark photons. Yeah. So basically, here in Brazil, we have an accelerator that is 3 GeV of electrons, but it's being used for everything except for particle physics. So we want to use it to particle physics. And in this case, we want to include a laser and through quantum, the inverse quantum scattering. Like here I show the two main processes, but in this case, the dominant channel is the T channel. And basically what we want to do is collide electrons with the photons of the laser and produce dark photons. And in order to see if we are actually producing dark photons, we want to include two techniques. That is photon counting and also missing energy technique. So in order to achieve the sensitivity that is below the EV scale, we need to include different technologies. And in this case, we are aiming to cover an unexplored area in other experiments. So if you want to see a full version of this world, it's already in archive, and you could see it in my Inspire Hub too. And yeah, we don't know what is dark matter, but I have one at home, so this is my cat. And thank you very much.
Thank you, Lucia. Thank you very much. Okay, so just a second, I'd like to say that you are very welcome here in International Institute of Physics. So anything you need to make you feel comfortable and to increase this environment for exchange, you just ask for us. We're doing our best, okay? And we hope that this speech talk make you curious, okay? And please, let's go to the coffee break. I think that Farinaldo would like to talk something. He's coming here.
So I'm just to like to know if someone is interested in joining the conference dinner on Saturday night. I need to know the names because I have to